So the discrete inf-sup, which is what we care about, we're going to solve a discrete system of equations. It's similar, except now P is an element of some finite dimensional vector space M that excludes the zero set, and H is an element of a finite dimensional space X that excludes the zero set. Then we have B U of H, P of H over where those norms in the bottom, I'm trying to do this without getting into functional analysis because I assume none of you have had it, except Michael's taking a class now. But these norms, I mean, really, if this is a math class, we would strictly define those vector spaces and equip them with certain norms and H1 and L2 and all this. Okay, I'm not going to bother with that. I'm not going to confuse you. It takes a lot more. And we won't need that necessarily for the arguments that are going to follow. This is equivalent to, and this is the way you'll see it a lot of times written. All right. So it's very, very hard actually to prove the inf-sup condition. Very difficult. It's not so difficult to disprove it. And sometimes to disprove it can also be useful from the finite element standpoint, right? We're going to select some finite dimensional vector spaces. These are our approximations, right? Linears, quadratics, right? We're going to select those in choosing the element formulation, okay? And so if we can at least look at our selection, and maybe we can't prove it's true, but often it's useful is to, say, disprove it or show a case in which it's not true, okay? And to simply, the easiest way to show it's not true is to find a B right there that's equal to 0. Right? If B is equal to 0, the right-hand side is equal to 0, and there's no positive constant in which this is true. Right? So,
for all arguments?
Well, yeah. Again, the non-trivial case, right? So you can't just choose zeros, but really, strictly what we'll say is that we'll find a B that is 0 for all U, right? So essentially, can we find a P that's also not in the 0 set, not a trivial one? Can we find a P such that B is equal to 0 for all U? And so let's consider the 2D domain so our domain doesn't really matter, but we can say it goes from 0 to 1 in the x and y directions. We're going to partition the domain into a set of finite elements of equal size, perfect squares essentially. Where the width and height is h. And each intersection will be nodes. Those nodes we'll use the index I for nodes increasing to the right, j for nodes increasing up, so that our elements will be numbered 1, 2, you know, I've only drawn 4 here, but that's not, you know, in general, there could be n minus 1 elements in each direction. N minus 1 element. Okay. It's a subtle thing, but it will matter later that h is 1 over n, with n being an even constant. We'll see why that matters later. Just to define some notation, if we have an element as I've drawn it, maybe I'll draw it red here. A node. This node is defined by I, H, J, H, right? It has the coordinates I, H, J, H. Okay. So let's first look at the integral of Kij, where Kij is the domain of the element with lower left-hand coordinates at I, H, J, H, right? So we'll just, you know, so this would be Kij. So it's just the domain of this element we're going to integrate over. And let's look at the divergence of V of H times P of H dx dy over one element. And the reason is, remember, if we go back here, this is sort of what we have. This is sort of what we have in this V term, right? So if we were to reconstruct the V operator from this thing, you'd have like some divergence of, you know, this is V dot, I'm sorry, V, right? So the function V of H is in U dot, right? I just don't want to carry a dot around, so I'm redefining V. So we have like the divergence of V, okay, and then P of H is in PP. All right, well, I'm just going to start on the next page. So I'll rewrite that. So we're going to look at the integral over the domain Kij, divergence of V of H, P of H, dx, dy. Right. Oh, I guess I didn't define, I have to choose a finite dimensional subspace. So the finite dimensional subspace we're going to choose, we'll go back to the other slide where I sort of defined everything. So the finite dimensional subspace we'll choose is P is going to be piecewise constant, and V is going to be piecewise linear. So piecewise linear in 2D, right, that's our quad, four-noded quad, right? Piecewise constant would just be a finite volume, essentially, right? P, so we'll have V1, V2, V3, V4, or the, you know, and then P1. So for every element, we'll solve for 4 unknown velocities and 1 unknown pressure over the entire volume. Okay? All right. So, since P of H is a constant, right? It's a constant over the domain. We can pull it outside the integral. And so for the ij domain, P will be defined at I plus a half, J plus a half, right? Everybody okay with that? The center of the ij domain. Okay? Now, so now that P's outside the integral, we're going to use the divergence theorem, right, to change that volume integral to a surface integral. So now we're going to integrate over the surface of ij, and because we use the divergence theorem, we'll get V in dx dy. Okay? Now let's remember, if we're integrating piecewise linears over surfaces, right? So if we look at the element Kij, on the surfaces we have piecewise linear shape functions, right? So if I want to integrate them, because they're linears, I can just use the trapezoid rule, right? So the trapezoid rule, so that the volume under each one would be 1/2 h times the height, and the height will be, so remember, this is the ij corner, right? So the height here would be V, and I'm going to use a superscript 2 to, so we're going to say that the vector V has two components, V1, V2, right? And where one is, this is the V1, this is the V1 direction, this is the V2 direction. Okay? So this point right here, this height, is V2 I j plus 1. And this one is V2 I plus 1 j plus 1. Right? So that's just this surface. We have to integrate over all four of them, right? So we'd have another one here. All right, so this one would be V1 I plus 1 j plus 1. And this one would be V1 I plus 1 j. Right? Everybody okay with that? So that's just the heights I've defined. And in every case, because it's h times h, in every case, then it's just, you have just a 1/2 h you can pull outside. Okay? So I'm not going to draw these two, but they just be the negatives of those at the appropriate indices. Okay? All right. So then, this thing is equal to, you know, integrating that exactly, this thing is equal to Pi, this is going to get a little tedious, but and that's the reason I put, because I need to reserve the lower left superscript. That's why I put the subscript over there. And I changed it 3 times in my notes when I was preparing it. I originally put it there, but then it looked like a V squared. I didn't want to put another indice down here. So this is the one component of velocity. All right, so So that's the integral of this expression over one element. So then B VH PH is the integral over the whole domain of that expression, which is equal to the sum from, sum over I, sum over j, from 1 to n minus 1, I guess I didn't explain, there are some constants, alpha and m from the Q matrix, but those are just constants, so I'm not going to carry them around. They're not going to change the outcome at all.
And there was there should be a thickness of the element outside of these, right? Like the edge.
Yeah, again, it doesn't matter. It's just a constant.
And when you're converting the left hand side to the right hand side, I mean, you should be cautious about that. Like when you have H.
As long as H is the same everywhere, it's not going to change the conclusion. So you can think of H as 1, right? Yeah. You can pull it out. Either way, you can pull it outside the integral if it's constant.
Yeah. I was wondering when we're using in the whole system, and we might have different.
But this is the constraint. We're only dealing with the constraint matrix, the Q matrix there. So yeah, I mean, there's like an H, alpha, M, but they're constants. They're not going to change what we're doing, right? I mean, you could just call them some constant, and we could carry it around everywhere. But it's not going to change the outcome of what's the conclusion. Okay, so then this sum here is equal to, if you just work through the details, it's equal to h squared, the sum over ij from 1 to n minus 1, v1 ij where I've introduced some new things, these partial 1ij sort of a finite difference stencil here. There's all these other H's on them. All right. So you'll notice that these things just multiply in velocity. And what we were seeking in the beginning is to see if we could find a P such that this equals 0 for any v. So if these two coefficients are 0, then that would be true, right? This would equal 0 for any v, because this is the first component of v, second component of v. So then, basically, if we equate these two, or set these two equations to 0, then we get two equations. Those two equations are and these two equations have a solution. The easiest way to write it is if you write P of H centered on an element Kij, the value of pH in that element would be minus 1 I plus J. Or, if we would actually look at what that is, and this is why the minus 1, I mean the fact that H was 1 over an even number, because the solution is what? This is known as a checkerboard pattern. And this is a spurious pressure mode. So, anybody ever solved the poroelasticity problem before? This comes up a lot, actually. If you don't know what you're doing, constructing the elements, especially in the drain condition, the drain case, boom, you'll get this checkerboard pattern in the pressure. And literally, you plot the pressure field, it literally looks like a checkerboard. If you did it in a finite difference setting, where, you know, in a finite difference setting, each cell, or a finite volume on a regular grid, you know, each cell is actually one color, right? It would literally look like a checkerboard. And it's because, so well before we had the mathematics, people did this and saw it. They didn't know why. Now we have the mathematics to know it. And the reason is that interpolation, piece bilinear on the displacements, constants on the pressure, violates the inf-sup condition. And we can also show that it violates it for probably what you would normally want to choose. So maybe since in this class we've mostly been dealing with piecewise linears, possibly your first thoughtless choice would be linears, bilinears in the displacements, linears in the pressure. Also violates inf-sup, and we can show that. So what do we use? And by the way, we did this on a regular grid, but remember, you can also prove it formally that, you know, the regular grid would just represent a parametric space for the diffeomorphism into the physical space via the mapping from parent elements to physical elements, right? So the fact that we did it on a regular grid, that doesn't change the answer. In an irregular grid, you still get the same thing. So what do we do? What can we do? What's a valid element choice?
Is that bilinear for U and bilinear for P as can?
Do what?
Is that P? So if we use the bilinear shape function for P, it wouldn't pass the inf-sup.
This is it's even more tedious than that, but you can prove that it's in violation of inf-sup. So what we'll use in your next homework assignment will be to code this up. Will be a biquadratic nine-noded biquadratic and a linear pressure. So 9-node biquad bilinear. So here and I say 9-node because if you remember the Pascal's triangle, as long as we're balanced, we have a complete set. Well, we could take an 8-node and then we'd be balanced. But we need that 9th node actually for inf-sup. So this has some sort of optimal constraint ratio, and we're inf-sup compatible with this. This is called like a Taylor-Hood element. You might see it in literature. No. The serendipity element's usually serendipity element is usually used. It has a mid-side. It would be an element that you'd use in a transition region, right? That from where maybe you're doing some kind of P refinement or something. You could use a serendipity element which have a mid-side node, but not maybe only on one side. Yeah, so I'll